Okay, we're going to talk about another concept that goes hand in hand with this. Just like we talked about electric field being the influence a charge has on the region of space around it, we have another concept we're going to talk about in terms of energy. So just like if we put a test charge, a little Q naught out here, it would feel a force, and that force would be in the direction of the electric field if the charge is positive. The force would be opposite the electric field if the charge is negative. We defined the electric field as the force divided by that test charge. So it's taking that little test charge out of the picture. The field still exists. There's still the potential there for a force to exist on any charge. Now we know as long as we're the same distance away from the overall charge that's creating the field. Oh, I got a little closer, sorry. As long as we're the same distance away, the electric field will be constant. It will have the same value, the same distance from this big Q. We're going to talk about another concept called electric potential. Now, it's very easy to confuse that with electric potential energy. This is potential energy. The energy is what a charge physically has because it exists there in space. We're going to take the charge out of the potential energy. So we're going to take our potential energy and divide it by Q naught. So taking this little test charge out of the picture. What we have left is called the electric potential. We use a capital V to represent it. It's in volts. So your batteries, you can go buy a 9-volt battery. We're talking an electric potential difference. There's a difference of 9 volts between the positive end of that battery and the negative end of the battery. Electric potential, if you want to compare it to gravitational potential energy depended upon how high the object was. The height was what mattered. You can think of electric potential, if you'd like, as an electric height, a height for your charge.
Quick question.
Is
Are coulombs, do they have some units built with other units?
coulombs will make up some other units. Coulombs itself is a fundamental unit.
Okay.
It doesn't break down into anything.
Because this volts says volts is based on coulombs.
Correct. So the units of this, energy is joules, charge is coulomb. So volt, electric potential is a joule per coulomb, which is a volt. Coulomb itself is a base unit, but other units can depend on coulombs.
Okay, so coulomb, just to be sure, it's not like newtons where it's like kilograms, meters,
Right.
blah, blah, blah.
But a volt is like the
It's just
unit.
a coulomb deal with it.
Mm-hmm. Exactly.
Okay.
Okay. So this location here, where these charges are equal distance from this big charge Q, they would all have the same amount of energy. They would have the same amount of energy between these two. It would be the same amount of energy between these two because they're all the same distance away. This surface, if I draw this surface, is called an equipotential surface, meaning equal potential. The potential, you can think of it as the height, the electric height being the same all along that line. So that means any charge placed anywhere on this surface will have the exact same amount of potential energy, no matter where I put it on that surface. If I come out further, this would be another equipotential surface. The potential is the same everywhere on that surface. Sorry, it's supposed to be round and centered on this guy. That means any charge I place anywhere on this surface will have the same potential. But will any of these charges on the inner circle I drew, will they have the same amount of energy as any charge on the outer surface I drew? No, the energy will be different. Which one has the higher energy? The one that's closer. Exactly right. So there's a potential difference between these. By that I mean there's a delta V. There's a difference in potential between those two surfaces. So potential difference is what we call that. As a charge moved from one of those surfaces to the other, as it moved through a potential difference, the charge's potential energy will change. Just like we have the potential is equal to U over Q naught, we can say delta V, the change in potential, is equal to delta U over Q naught. So the change is the same. So the value of the potential at any one point is the energy divided by the charge. The change between any two spots is equal to the change in energy over the charge. Which in turn, by the way, means delta U, the change in energy a charge experiences, is equal to Q naught times delta V. Just rearranging this equation. So anytime a charge moves through some sort of potential difference, its potential energy changes. Now, by the way, using this relationship, the electric potential created by a point charge, well, if we take the energy for point charges and divide by a Q naught, it's really easy to find the electric potential around a point charge. All you need to know is how much charge it has and how far away from the charge you're interested in.
It doesn't matter the strength of the center charge.
It doesn't depend on, it depends upon the strength of the center,
But not the
but
charge.
not the test charges that are going to have the energy. So by big Q, I'm trying to represent the one, the central one, the one creating the potential. Okay. Nice thing is too, if you have multiple charges and you want to find the potential at some point due to all of them, you simply add them up. And it's not a vector, which is fantastic, because there's no x and y components. So you simply add up the values you get. Questions so far? We're going to be carrying this idea of potential through as we start talking about circuits. When we talk about how a circuit works, we talk about potential differences. I mean, to make an electric circuit work, you either need to put a battery in it or you need to connect it to the wall outlet. A battery, a wall outlet, has a potential difference. Now granted, the wall outlet's potential difference is changing with time. It's a sinusoidal function, but there is still a potential difference. It's this potential difference that is creating the force on the charges to make a move, and in turn creating a current.
So this kind of says that the terminals of a battery have an electric field.
Yes, when you connect the terminals of a battery to each other by some sort of wire, it creates an electric field, yes.
Well, I mean, a disconnected one, because what would be pulling, like, if the batteries are disconnected, does that mean there's a field there that the voltage is a potential something, so if there's a
Right.
charge, then it's going to move.
There's a field inside the battery as well, yes.
But, I mean, the nature of a battery, it's not going to take unless it's getting the same
Right.
times.
Exactly. And so the battery itself, in order to harness and cause that electric field to do work, you need to complete the path between the two ends of the battery.
Okay.
But that's a good observation though. Wherever there's a potential difference, there's an electric field. The two go hand in hand. If you have a potential difference, you have an electric field. And by definition, the electric field will always point starting at a high potential value and will point down towards low potential values. High potential values towards low potential values. The potential gets weaker and weaker and weaker as you follow the electric field line.